so we turn to the proper calculus of parametric curve. So actual derivatives. For derivatives, however, we need to look at the limits. So even before, I don't want to give you the impression that it is the essence of calculus is the limits, even though it is common point of view. But really, what we have done recently actually points out at what is, in my opinion, the essence of calculus. This is so it is a change, a rate of change, in all of that business, even before we get to the limits. Okay, so we did this before limits. So this is about parametric curves. Remember what has happened? It was we set up the physics of the problem, which is simply the acceleration, vertical acceleration -32, horizontal 0. Then, based on that, we computed the numerically. So we did not do any actual calculus. No differentiation or anti-differentiation happened here. We do it in a pure numerical way, as you can see here. This is the formula. Remember, which amounts to this computation over here amounts to computing it is doing a Riemann sum. This is a Riemann sum, so suppose this is the derivative. What's happening every time you add, and then how do you get from here to there? You compute you multiply the derivative by the increment of time, and that gives you the extra value to be added to your value of the function. And that's how you progress. So that is the imagine this is the subdivision of the Riemann sum over here, and over here is the actual value as you build up, and remember those bars. The adding little by little produce this result. Okay, so and then we did the same exact thing with the next step from velocity to acceleration. I'm sorry, from velocity to location, and that's the location is the result. But you can actually see it. Let me make that point clear. So, like I said, this is in the formula is the same, as you can see. Once again, exactly the same formula, which amounts to Riemann sum. In fact, to make that point clear, I could do this. Let me at least try. So this is the velocity of y, and I will insert another chart. And the chart is a different kind. Okay, so, well, I guess they don't quite understand what's going on here. Let me try it this way. Yeah, so that, okay, maybe this one. Maybe this one, no. Yeah, so it's not especially good at it. Well, the point being is that these, I didn't mark the right one. Let me try again. So these are the values of t, the independent variable, and here I'll plug the values of the derivative. Okay, so maybe that might help. Okay, well, for some reason it's upside down. Yeah, no, let me try again. This one. This one. No. Okay, well, so it didn't work out that part. So the values of x here, integral, and the value of the derivative here, and over here in that row we produce the function itself, which is produces this curve. So it's anti-differentiation. There is no literal integration. So all these rules that you have learned in Calculus 1 and Calculus 2, how to integrate functions, all of that does not come up. There is no actual derivative. There is no actual antiderivative, and there is no need for limits, technically. Strictly speaking, there are no limits here involved. So the point being is that is this calculus? Certainly it is. Does it require limits? It does not. So it is, in fact, the setup that precedes the limits. And then if you need an infinite precision in your developing a theory of whatever physics or any other theory, then you need limits. Okay, you need limits, you need derivatives, you need antiderivatives. Okay, so that's what Calculus 1 is about. But once again, you start over here with pretty much numerical computations with the assumption is that during each of the time period, like here, there is no change in, say, velocity. Okay, there is no velocity. If the velocity does not change during this interval, it means that you can compute your next location pretty much by multiplication. Okay, so but then for absolute precision, you take limits of those functions, and you have all of these computations that provide you with instantaneous velocity, instantaneous rate of change, instantaneous velocity, and derivative, and then antiderivative. You know the rest of the story. Okay, so once again, just the point being is that these are the three steps that you start with calculus. Numerical computations, which is approximate. You can do a lot of stuff with it. Actually, I was going to show that if this doesn't look like calculus enough, or maybe not, this is what we did not too long time ago. So this is called two-body problem. So you can think of, once again, you have two celestial bodies, and they're moving around each other, and well, I'm sorry. So, just a minute. Okay. Okay, so things are getting more complicated. Options. Okay, options. Options. Formulas. Enable iterative computation. 1. Okay. Okay, so now let's see. Okay, so once again, the same thing that we did in class. This is just slightly more complicated because the interaction between the two bodies is based on the neutral law of gravity rather than just plain pulling you down. So these two pulling each other towards each other, and the formulas are here. You can see formula here and formula there. They are pulling each other, and that's the sizes are comparable. One is 500, the other one is 300. That's why the sun is not. You can't even think that it is standing there somewhere, not moving, and then pulling the Earth around it. Okay, so they are dancing around each other. You can see that. If you see that little cross over there, that's the center of mass. You see the cross, the little mark over here? Okay, so they are dancing around that center of mass, which is moving slowly in a certain direction, roughly like this. So once again, it's done all with nothing but this little algebra, so there is no actual computation. And you can solve a lot of problems in a purely computational way, even before you get to any kinds of limits. Okay, so, and then you can see how things are happening. That's very fascinating. Okay, so that was just the point I was making. And now we still do have to turn to limits eventually, because for our precise computations. So for example, if you want to demonstrate that you can solve the problem, the answer for Newton's solution that they're actually both bodies are still orbiting not either one. So the Earth is orbiting the Sun, but in this case they are both orbiting their central mass. Okay, so they are still, if you fix the central mass, then both of the bodies follow still the elliptic orbits. Okay, so to produce that result, you can guess that result by observation, as we did, but actually you could, and in fact maybe, yeah, that's pretty much it. Let's see. Yeah, so this is what's happening. The center of mass, I put the center of mass in the middle, right there, okay? And you can see there, if you look at only one of them, well, does it look like it's falling on an ellipse?
Yeah.
Yeah.
I'm just curious. It looks like the center of mass is moving. Can you so constitute the relative masses of the two objects that the center of mass, as it moves, traces out a closed loop?
No. The center of mass is moving along a straight line at constant speed. So because because you remember they cannot, any change in speed or in velocity rather, is you need a force. Okay, so to outside force, and this is only the system itself has only interior forces, so it cannot from inside pull it off that straight line. Okay, so it does look like these are the conjecture is correct, that both of them are moving along the roughly the same elliptic orbit. But to prove that is the case, the way Newton did, we would have to do derivatives. So even though this is certainly useful, this one useful tool in your projects, I hope you pick one of those for your project. So we'll get to the project after the midterm, I think, because it's just too close, and then we'll think about it. Okay, so parametric curves. This is the nature of parametric curve. The typical curve is the circle. We'll look at the limits once we know why we study calculus. It's just to study rates of change and so on, and velocities, accelerations, and similar things. Primarily in physical spaces, but certainly you can think of things like that happening in abstract spaces. They just look harder to understand. So physical spaces where we live in, and we understand the motion as as we're living in it. We know roughly what it means. What it means to move through our world, to move through a space of prices. I don't know what it means, so you probably need to live longer than that, or just have a good theory for it. So, okay, so calculus 1, we will translate all the ideas from calculus 1 into parametric curves to begin with. They will look very similar, just a little twist that needs to be done. And as you can see, we end up with the definition of continuity, which mimics the definition of not continuity, the limit, the idea of limit of a function of one variable. In fact, if you have a graph, you zoom in on that point, not necessarily you would be able to tell whether or not that curve is the graph of a function, or it is the trajectory of a parametric curve. Okay, so and then that's how we transition from one to the other. So it is to realize that x and y possibly independently approaching two different values, and that if we pull A and B over there, if we put these two together, then the convergence will be either of points or of vectors towards either point or a vector in that two-dimensional space, or high-dimensional space as well will look exactly the same. That transition is maybe I skipped that a little bit too quickly, but I just want to remind you that how we transition from one to the other between points and vectors, especially in high dimensions. It is so if I have a vector, if I have a point P, then I can transition to a vector OP, right? So for every point there is a vector, the end of which is a vector. Okay, and then and similarly, if you have OP, the vector OP, and their all vectors will be starting at the same point, the origin, then you can certainly just record that point, and you have your point, that correspondence that goes back and forth, and then naturally the correspondence is between also between coordinates on the left and components on the right. Okay, it is the same. The theory of calculus can be done with both. The limits can be done with both, but there is this little difference that I try to emphasize, that the fact that even though it's interchangeable doesn't mean that you can pick one and stick with it. You actually could. If you take your book, I believe the book picks this one. So everything is a vector. There are really no points. But you know, if you have something for vectors, then you can translate the language into the language of points. Distances are changing. Distances between 2 points become magnitudes of differences, and so everything is interchangeable. But there's subtle difference, and sometimes it's helpful to know whether you're dealing with allocations or vectors, and especially when you talk about derivatives or motion. You know, motion is technically it is a point. You have a location. It's not a vector. If you have two locations, you don't want to do algebra with them. So, but on the other hand, the velocity is kind of a vector. Okay, so all right. So we'll get to that soon. But right now is how do we explain those arrows? So these arrows are familiar, right? These are same arrows. Because these are numbers. So t goes to t naught. We know what it means. It simply means that. Well, I don't want to. Well, I could just write just as well. T minus t naught is going towards 0. That's how we can explain. Everything can be explained in terms of distances. So that's why we make such a big deal about metrics and the way of measuring in the multi-dimensional spaces. But this is one-dimensional space. This one is high-dimensional space, Rn. Okay, so that arrow is new, and then below we explain what that arrow means. It's either the distance between these 2 points, p. It is a point that depends on t, right? Points that depends on t, and then what does it mean that p is approaching a? It means that the distance between those 2 points is going to 0. Okay, so if we're talking about the vectors, we take the difference of the 2 vectors, and we look at the magnitude of that vector. Okay, so this is which way? So that's u minus u. Okay, and okay, so the point is then that we were able to reduce the problem of limits in the multidimensional space to the problem of limits of numbers. So why? Because these are numbers. So even though PA are points in multidimensional space, V and U are vectors in multidimensional space, once we apply either the distance or the magnitude, the result of that operation is a number. Okay, so, and then we know how to deal with limits of numbers. Well, I don't have to tell you, it is calculus 1. So the computation itself might be a bit of a challenge, but really it's not a big deal. And at this point, probably that is the abstract explanation, but probably a good idea now to look at the coordinates. So, for example, if, as I said, dPA is going towards 0, okay, so I use the distance formula, Euclidean metric. So it will be, say x. Well, let's go to dimensional. So it will be x minus a squared plus y minus b squared. Square root is going towards 0. Here, so p is xy. It is a point. It is a variable, depending on t possibly. And a is that point ab fixed. And what we're saying is that as t approaching t naught, p is approaching ab. So so we now explain that arrow above with the new notation or the recent notation of the distances in next line. And here we write out that the distance notation in terms of actual coordinates of the point. And that's what we get. And let's now investigate what this means. And so that expression is going towards 0. The square root of a certain expression is going. I want to take it apart. So an expression, the square root of an expression is going to 0. What does it mean? Can we simplify the expression?
You just take the square root of it.
We could remove the square root, and I wonder if you can justify that. I want to remove the square root. So what the claim is that these two statements are the same, even though the second one is simpler. Can anyone justify that transition? Removing the square root?
Is it because it's going towards 0?
Well, it is going towards 0, yes. So certainly if this goes to 0, this number has got to be the same. But why does the square root not make any difference?
Is it square 0 and it's still 0?
Well, that's what I meant. So if we have 0 here, we got to have a 0 there. Yes, because the square root of 0 is 0, yes. So if this one is going to, well, okay, if we go backwards, suppose this thing is going to 0, why does that thing go into 0? Because what?
Because the square root of 0 is 0?
Right, yes, it's half of the answer. The functions and limits, I remove the function from consideration. Okay, maybe it will help if I write it in terms of, with LIM. So, LIM, say, of, well, that maybe, yeah, t goes towards t naught, some number, x minus a squared plus y minus b squared is equal to 0. On the other hand, I have this without the square root. So why can we remove the square root so easily?
We could reason that since both of the terms in the bottom there without the square roots, since they're both squares, they're both non-negative. So unless x goes to a and y goes to, or if either x didn't go to a or y didn't go to b, if those two differences didn't become arbitrarily small, then that bottom limit wouldn't go to 0.
Well, you're making an implicit use of a certain fact that I want to bring into the fore here. As you can see, I'm removing the square root. Here, this square root was inside. Now it's on the outside. How come? Well, this is okay because because the square root is a nice function.
Because it's continuous.
Because it is continuous. So some things are really important that we're going to be relying on from calculus 1. We're going to be relying on, even though we're going to have analogs of those statements in this for parametric curves, but most of the time there we will take them intact, and so they are really very basic, even though the entities we're dealing with are much simpler because they're just functions. And that's the idea of continuity of a function of one variable is in fact very important in this continuity when you compute limits. It is the composition, and you can pull out a function out of composition. That's what happened here if the function is continuous. Okay, in fact, well, just technically it's continuous from the right, but that's okay. It is continuous from the right. That's it. That still works. So, so the limit of square root, this limit of the square root at 0 is equal to 0. That's another way to explain, but it's a little bit longer. So the limit of square root of, say, u is going to 0 is equal to square root of 0. Okay, so this is the definition of continuity, right? The limit of the function is equal to the value of the function. So whenever you have a limit and you start talking about the value of the function that you were dealing with, it means that you're talking about continuity. Okay, so the function is continuous because, well, this is the explanation. This is the graph. This is 0. And as you can see, even though we are approaching the value of u here is approaching 0, we get into the definition of continuity, but the definition of limit, but rather we just say the magic words. The function is continuous, and that's why its limit is evaluated by substitution. Remember, that was actually called the substitution rule. Function is continuous. How do we evaluate the limit? Substitute. That's what happened here. That's what happened here. Okay, so anyway, so that's very nice that we were able to eliminate the square root out of the consideration. And then now, but we're not done, because I want to draw more conclusions from this. So let me proceed on. So I have to repeat. This is what I have as t goes to t naught. So two numbers. The sum of two numbers is converging to 0. What does it tell you about these two numbers, considering that both of the numbers are positive? The sum of two non-negative numbers converge to 0. What does it tell you about the two numbers? You see, they cannot cancel each other.
The individual parts are
Yeah.
approaching 0.
Then both of the parts would have to also go to 0. Okay, great. So we split our multidimensional or vector representation of the problem into two coordinates treated separately. That certainly is the any kind of computation will be based on that idea. But there is more to it. So x minus a squared goes to 0. I replace it with what?
X minus a goes to 0.
X minus a is going to 0. And y minus b is going to 0. Because the magic words. What?
Squared functions continue.
The square is continuous. The square, so u squared is continuous. So once again, we're getting rid of the square. So I sort of take the square root of the well, you can say square root is continuous. That would be just as appropriate. And then I simplify my limit. So doing any algebra with limits requires using rules of limits or rules of continuity, and this is one of them. And then we realize that really everything is happening separately. So if this is my A and this is my B, then if I split these two, then the behavior of x is here somewhere. So that's x going towards A. In the meantime, y is going towards B. If we take this together, then we form some kind of a rectangle. Okay, so with that is getting smaller and smaller and smaller. So all my points on my graph will be lying here somewhere, maybe this way, that way, even a vertical. It could be vertical just as well. As t gets to t naught, that rectangle will be getting smaller and smaller, and that's the meaning of the limit of on the plane. Okay, so the function, the parametric curve, will be converging, as that's what we started with. Will be converging to a particular value. So AB, right here, where it is. Here it is, to a particular value AB, if each of its component functions converges to respectively A or B. Remember, a parametric curve is nothing but two functions, and I just use here for convenience over here. I'm using the same name for the variable x as well as for the function. So those are the two functions is what I'm talking about. This is my parametric curves, two functions, x is a function of t, y is a function of t, and then it turns out that all I have to do is to understand the limit of the whole thing is just to look at the two functions separately. Okay, so let me state this explicitly. So p of t, let's say I want to make it to L, standing for the limit as t goes to t naught. If and only if x k of t is going towards L sub k, where where these are the component functions. So P is x1, x2, xn. So this is in Rn. We have a parametric curve in Rn, and we have a convergence to a particular location. So L is a point in Rn, so it is with coordinates L1, L2, Lk. Okay, and then how do we assure that the whole thing converges to that location? So it could be two-dimensional, three-dimensional, any dimensional. That's how we just ask every coordinate function to converge as well. Okay, so and then vice versa, if you have such a convergence within each of the component functions, then you have the convergence of the whole thing. Naturally, it applies similarly to vectors. So let me state that just in case. So stating the same thing, but for vectors. So we have a P of t. This time it is a parametric curve. Let me call V of t as I have in the past. V of t converges to some S. As t goes to t naught, we can have the if. V sub k of t is going towards S sub k, where V is a vector with components V1, V2, Vn, and S is also a vector with components S1, S2, Sn. Okay, so certainly the I state these facts or definitions for the first for the in the abstract setting, in the setting of points and vectors, without specifying location, specifying coordinate system, and then it is when you try to state it in the referring to any particular coordinate system, it becomes kind of complicated. It becomes longer. You get the dot. You have n-dimensional spaces. Because if you look at what we started with, it is actually much more compact. This is a pretty compact way to describe what we're talking about. But this fact is really necessary, however, whenever we do actual computations. It's really not, well, let me state then the definition, and naturally the definition of a parametric curve. So a parametric curve, P of t in Rn is continuous at t is equal to t naught if that part of the definition is exactly the same. So the limit of p of t goes to t naught is equal to p of t naught. So, in other words, substitution. Same rule as in calculus 1. The continuity of a function means that you can evaluate it, that its limit by substitution. Say, limit of sine t cosine t, my curve with t is going to pi over 2. So how do I compute it, practically speaking? Well, how do I compute it to verify the continuity of the curve? We certainly do know that it's a curve, it's a continuous curve, but how do we know? We compute the limit, and I do it, how do I do it? I do it by one component at a time. So in fact, I have to compute the limit according to the previous statement. I have to look at limits of each of the components functions, so I'll compute the limit of sine, and the limit of cosine. Okay, and there you go. And then at this point, this analysis of component-wise component-wise, taking limits component-wise allows us to reduce whatever we have to understand now about new functions in terms of one-dimensional functions, therefore rely entirely on calculus 1. Just that is the transition. That's the importance of that result. Okay, so what do we do here? We compute both of the limits using what you know from calculus 1. Okay, so what do I write here?
1, 0.
I want to stretch it a little bit. You can certainly do it. You're skipping maybe one step, but let's do it one at a time. So it's supposed to be 1. Why is it 1? The first one.
That's what sine pi over 2 is.
That's right. So sine pi over 2. Okay, indeed, and well, in this one, cosine pi over 2. Okay. Before I move on to actually compute these numbers, I make the comment. What's the comment?
They're both continuous.
They both continue. So once again, magic words. Why do we evaluate limits without evaluating limits by substitution? Because the functions are continuous. So because sine and cosine are continuous. Okay, so and then sine of pi over 2 is 1, and this one is 0. Okay, you certainly, any particular choice of pi over 2 was arbitrary. I could pick any other number and carry out the same computation with the same exact logic, and every time, and then I will once again observe that the computation of the limit will be reduced to simply substitution because the two functions are continuous. Okay, so based on this idea, what is the relation between continuity of a function of a parametric curve and continuity of its components? What's the relation?
The parametric curve is continuous, I guess, and only if each of its component functions are.
That's right. So that's right. So this result is what it gives us. So the limit r exists and equal to a particular number if and only if that exactly the same thing happens within each component function. So then we have the same about continuity. So let me state it exactly as it was suggested. So theorem, parametric curve in Rn is continuous. Once again, I want to do it one point at a time, just the way it was done in calculus 1. If not, if and only if its component functions of one variable, one value are continuous at g equals 0. Okay, so that's an example function. That's what it looks like, made of two functions, regular functions. And then the continuity of this is equivalent to the continuity of both of these functions. Okay, so if you write any kind of formula, sine and cosine, for example, as long as those two functions are continuous, then the whole thing will be continuous. And naturally, what you would think is that you're going to have, you probably can guess that the curve that traced by my parametric curve will be also a continuous curve, so there won't be any breaks. The reason for it is you'll be probably better idea than to explain why the curve will be continuous is when the two component functions are continuous. You probably would have to build the in addition to x and y, you will have to build the curve. Rather than the parametric curve, you will have to plot the graph of this function with t, x, and y, and and then make an argument that the continuity of those two functions with respect to with respect to x and with respect to y are continuous. It's like you're moving here and you're tracing out continuous curves on the x-axis and on the y-axis. Then it means that if you take t out of consideration, the curve will be still continuous, because it's like a curve that is in space like this, in the three-dimensional space, tx and y, and then to plot the path, you sort of collapse it like this. Naturally, when you do the collapse, in other words, for instance, projection, when you collapse it, what it means that there are no breaks. You're not going to break anything, which is still to be discussed. And then if you are breaking, so the curve will be on the xy plane, will also be a continuous curve. So, for example, for the circle, remember for the circle parametric curve, so its path or trajectory is a circle, but its graph is in fact is a helix. So, in other words, ascending spiral. Well, in this particular case, t is facing us. That's why it's going to go roughly like this. Okay, so if you let t point at you, then you will see nothing but the circle. But if you look at it from the sides as this, you will see that's like a spiral. So like this. Yeah, I'll do Excel at some point. Excel, unfortunately, doesn't do three-dimensional plotting a lot. Okay, so that's roughly what the graph of the circle looks like. Okay. Okay, I wanna state this one more time. Is the idea of the limit. So limit p of t is equal to, say, L. T goes to t naught. Okay, so if I try to take it apart, I just want to mark, okay, I'll mark the numbers in green. These are numbers. And then I'll mark some numbers. And then I'll mark vectors in red. So these are vectors. Okay, so as you can see, the green is the input of our parametric curve. It is a number. The output is p, is a vector. The change of the independent variable is under LIM. Okay, so still numbers. That's familiar. And then the output of our limit is another vector. Okay, so now similarly, we've now explained what it means by pretty much the definition. I'm looking at let's do limit of the magnitude of p of t minus L equal to 0. T goes to t. So the notation is at the top, the first line. The last line is the explanation. Why is it explanation? Because it reduces the problem of limit in multi-dimensional space to limit of numbers. So let's confirm that. I'm circling again numbers here and numbers there. Are there more numbers in the second line?
The whole magnitude is a number, right?
This is a number. That's right. And this is also a number. So that's what I mean that we reduce to calculus 1. So even though I could still mark that this is a vector and that is a vector, these are vectors, yes. But once you carry out this computation, what's inside our limit is a number, and the output of the limit expression is still a number. Okay. So we're explaining vectors with numbers. So there are certainly discontinuous functions, just like calculus 1, but I don't want you to think too much about those, and just know what you remember from calculus 1, and well, give me a discontinuous function from calculus 1.
One over x.
Okay. y equal 1 of x. So you might be asked to then, what about discontinuous functions? What about discontinuous parametric curves, right? So that should not be a big deal because we can convert every graph, every function of one variable, y equal 1 of x, to parametric curves. So remember the strategy for that. Okay, maybe we'll talk about that. It did not come up before. So first of all, parametric curve is two functions of one variable from calculus 1. So real value to real variable function. So P of t is once again paired out f of t, g of t. Okay, so it looks more complicated because there are two functions. Okay, but conversely, however, it is not too hard if you already have. So that's the conversion from two functions to one parametric curve produces two functions. So you can go back and every time into calculus 1 and you have two functions to study, which is just we just did a minute ago. But if you are all you are looking for is some kind of examples to bring from calculus 1 to calculus 3, then it's not too complicated. I go with, say, y is equal to h of x. So the question is, problem, find a parametric curve, the trajectory of which, well, it sounds too complicated. How about we just say a parametric curve, well, parameterize its graph. That's the way to put it. Okay, so the graph might look any way you can imagine, but still entirely calculus 1 problem, y equal h of x. And parameterize the graph means that find p of t, once again, two functions f of t, g of t. As you can see, the original setting, there is no t. There is x and y, nothing else. Okay, so you need to find f of t and g of t such that the graph of the original function, y equal h of x, is the trajectory path of p. So in other words, you have a road looking like this on the xy plane, drive through it. And how you want to drive through it is entirely arbitrary, and the answer is, okay, just 1 second. So the answer is f of t is t, and g of t is h of t. Okay, so that's the answer. So as you can see, you can always pick the first function, very simple. Okay, so you're moving at the uniform speed along the x-axis, and the g function gives you the y-axis, y-coordinate. Okay, so we'll continue. Next.